Hello, everyone. Happy New Year. This is the first of our event for 2022. And we are very happy to meet again online. We hope one day we'll be able to organize these activities in person and fly in some people from the United States at some point. I won't be long in my introduction. I am going to recall everyone of what the cluster is about, what these talks are about, and then I'll say a word about our guest speaker today, and we'll have more time to interact a little later. So this is the cluster on technological change in society. The cluster is an interdisciplinary center within the EUI that tries to work across the various disciplines of the EUI, which are political science, economics, law, and history. And we're basically here to look at a topic of common interest with interdisciplinary eyes and backgrounds. Now, in order to foster this ambition to be more interdisciplinary, we in this particular cluster, we decided to invite to our activities not only people from our various fields of research, but also people from more distant fields of research. And this is indeed what's going to take place today, another time. For a common understanding to be here again, this is an audience of mostly social scientists with very little knowledge of hard science. We try to understand each other, we try to develop a common language, we try to enrich each other of various perspectives. So this is what we're trying to do. So for this particular talk today, we have decided with my colleagues in the cluster, the researchers who help us organize the activities, but also the other co-directors, Professor Calzolari and Professor Sartor, to invite Dr. Sofia Sheikh, who is a postdoctoral fellow through the SETI Institute. Dr. Sheikh benefits from a National Science Foundation Ascend Fellowship in this context. She studied physics and astronomy at the University of California, Berkeley for her undergraduate education and completed a dual PhD in astronomy and astrobiology at Penn State. Sofia, if you allow me, Sofia, I'll use your first name. Sofia has worked with the Breakthrough Listen project at the Berkeley SETI Research Center. And she's developed there a very keen and strong interest into radio astronomy and the search for technosignatures. In 2019, I believe, she was one of the authors of a breakthrough paper on BLC1 that was published in Nature Astronomy. And this paper is a very important contribution, and we'll post a link to the paper in the chats. Now, to give you some context about Sofia and the kind of effort she's involved in and the kind of environment she is surrounded by, Sofia works at SETI, and I was doing a little bit of research on SETI, and I realized that it's a fairly I would say old and established research institution located in Silicon Valley that is very close to the NASA Ames Research Center. The SETI Institute was created in 1984, so it's been there for a while, but I think the most salient and important fact that I have to share here is the mission statements of the Institute. So allow me just to quote from random searches on the internet. The mission of the Institute, quotes, is to lead humanity's quest to understand the origins and prevalence of life and intelligence in the universe and share that knowledge with the world. Research at the SETI Institute encompasses the physical and biological sciences and leverages expertise in data analytics, machine learning, and advanced signal detection technologies. So this is to situate a little what we are going to talk about, and to also situate our guest speaker, who is a strong asset and part in the effort and ambition of the SETI Institute. So Sofia, I won't be long. You've accepted to come today to talk to us and enlighten us on the topic that you have titled, on a talk that you have titled, "The Search for Extraterrestrial Intelligence, Hunting for Technosignatures in the Past, Present, and Future." So we are absolutely delighted to have you here. As I said before the talk, please bear with us if we do not understand enough, or if we are slow in our understanding of what you're going to tell us. We are very curious, and we are really here with a learning mindset. So the floor is yours, and thanks again for being with us.
All right, thank you so much for that introduction. Am I coming through all right?
Yes.
All right, perfect. So good evening to all of you. It's morning to me, so I have my tea. And I'm really honored to have been invited to give this talk. So thank you to the organizers for reaching out. And this is kind of a unique opportunity for me as well. So I'm going to do my best to sort of match my talk to a level that will work really well to facilitate interdisciplinary discussion. But if I fail in that quest, which I'm sure I will at some point, please just let me know, and I'm happy to explain more about anything I'm talking about. So with that, I am going to hop in. And first things first, when you hear the search for extraterrestrial intelligence, or sometimes you'll hear it abbreviated as SETI, a lot of people kind of imagine that this is a little bit science fiction-y, right? But SETI is grounded in some very traditional strong radio astronomy, and has been around for, at this point, going on 60 years as a subdiscipline. So I'm going to talk about a lot of that science background, the foundations of the field, why are we searching, how are we searching, why do we think that's the best way to search for intelligent life elsewhere in the galaxy or the universe. And then I'm going to move on to talking about some of the ethical and policy implications, at least that I'm familiar with within my field, and give some context for the sort of questions and challenges that we wrestle with as scientists doing this work. So, as I already referenced, when you say aliens, or you tell people you're looking for extraterrestrial intelligence or life, pop culture has given people a lot of ideas about what that would look like. And so here are some of my favorite media and pop culture aliens. But in general, when we talk about aliens to the general public or to people outside of our field, they all picture something that has something in common. And that's that the aliens that they picture are not usually microbes or fungi, but they're usually some sort of sentient being that we can relate to as some other human-like creature. Not always, but a lot of the time. So one way that you might see the search for life elsewhere framed is by this question, are we alone? But I'd like to dig into that a little more, because when I say that, I would be thrilled if we were to find microbes on another planet in the solar system, which so far we have not. Earth is the only planet that we know with any sort of life at all. So yeah, I would be happy with microbes. But most people, when they hear this question, are really thinking of something more like Star Trek's Mr. Spock. They want to find something in the galaxy that they can relate to, that they can talk to, that has technology or culture or art or any of these other sort of definitions of some sort of human-like sentient life. And often we summarize that desire by saying we're looking for extraterrestrial intelligence. But I want to draw that into question a little bit, because we have all sorts of examples of intelligent species on Earth, from octopi and squids and other cephalopods, which I believe were recently kind of elevated in status as creatures that should be protected due to their intelligence in the UK in a pretty recent ruling. And Then you also have cetaceans like whales and dolphins that have developed extremely complex languages. Birds like parrots and crows have language and also exhibit tool use. And then evolutionarily, very close to us, primates, especially chimpanzees, show a lot of tool use behavior, social structures, and other things that are defined in the animal and ecology world as intelligence. I added the microbe to this slide as well, because even single-celled organisms, as they work together and network, show emergent behavior that is much more complex than the individual creatures that kind of comprise the network. So all of these things, by different definitions, are examples of intelligent life on Earth. But if we tried to detect any of them at interstellar distances, with the exception maybe of microbes, we would fail. And so really, we're not looking for extraterrestrial intelligence, even though that's in the name of our discipline. Truly, we're looking for extraterrestrial technology. And we use the technology as a proxy for intelligence. So now I'm going to clarify and say, okay, how many technological extraterrestrial species are there? And now that's a research question we can start to try to answer. One way to go about that is to use this framework called the Drake equation. And so this equation was invented in the 1960s by Frank Drake, so eponymous, at the Green Bank Observatory in West Virginia in the United States. And Frank Drake had gotten together this group of about a dozen experts, interdisciplinary experts, but across mostly the science fields, to start thinking about this question of life in the universe. And at this workshop at the observatory, he ended up coming up with this framework. And I want to step through it here from left to right, because it's something that really guides our thinking in SETI. So the thing that Frank Drake was interested in was this variable n, which is how many civilizations are there in our galaxy with which we could communicate right now? That's the thing he wanted to know, the research question. And that's a big question, and it's difficult to answer. And so the way that he framed this was saying, okay, well, we know on Earth, we had to have the sun. We needed a star to evolve around that gives us light and heat and allows life to evolve. So how many stars are created every year? And those are going to be the sites that we're interested in for trying to break down this question of how common life is in the galaxy. And again, on Earth, like I've already kind of given the answer there, on Earth, life evolved on a planet. So you need a star, but you also need a site for life to develop. So some sort of planet with a solid surface. How many stars have planets? And then of the ones that do, we have planets like Earth and Mars in our solar system, which are kind of terrestrial balls of rock that we can stand on and interact with. We also have gas giants like Jupiter and Saturn, which you can't even stand on. You would fall right through to the center. So we want to know for the planets, how many of them could develop an ecosystem like Earth? How many of them are terrestrial planets that are the right temperature to have maybe water on their surface? And then it gets a little harder to define. So once you have a sample of planets and you're like, okay, all of these are sort of like Earth 2.0s that look very similar to Earth, could develop life, have all the right conditions, how often does life develop given those conditions? And then the next factor here is, okay, we had microbial life on Earth, tiny microbes and bacteria for billions of years before that life evolved enough to become the intelligent species we see today. So how many planets does that process actually happen on, and how many of them just stay as kind of surfaces of bacteria and slime? And then, as I've talked about, there are intelligent species on Earth that haven't developed technology, at least not in a way that covers the entire planet in the way that human technology does. So that's another jump. How many of those intelligent species actually develop interstellar communication? And then now, okay, that's basically the question we wanted to answer, but we have one additional factor here. And I can talk about this in a bit more depth if anyone's interested in how you actually plug numbers into this. But the very first term here is a rate of star formation, so it has a time component. And so to balance that out and get a number, we need to have another time component. And the time component here is how long do such civilizations survive and continue to send out communications that we could detect. So the first couple terms in this, R star, FP, NE, we actually know the answers to now pretty well. The first two, we know to quite a lot of precision at this point, based on work that's been done over the past couple decades. The number of planets that could be habitable in each stellar system is still somewhat of an open question, but it seems these three terms seem pretty promising altogether. Signs are pointing to there being a lot of planets out there in the galaxy, around sun-like stars, around smaller stars with longer lifetimes. But then once you get to the second half of this equation, there's a lot we still don't know. And so we need more work on synthetic biology. We need more work on things like paleobiology to understand how life developed on Earth, to really get a handle on all of these factors. And then L, the lifetime of a civilization, is very difficult to understand because we have been sending out radio transmissions from the Earth for, you can say about 100 years. But if L is 100, it's going to be very unlikely, unless the universe is teeming with life, that we're going to be around at the same time as another civilization, if they kind of appear and die like mayflies. On the other hand, if L is 1 billion years, if intelligent technological life evolves and then sticks around for a very long time, then it becomes much more likely that we would run into another civilization and be in the same timeline, basically, the same place in the timeline. So some people try to plug numbers into this equation and see how many, what the estimate is for how many civilizations they get out the other end. I don't find the equation particularly useful in that sense, because there's just so much we don't know that by changing your inputs to be optimistic or pessimistic, you can get sort of whatever number you want. So for me, the Drake equation serves much more as sort of a conceptual aid to nail down, like, here are the areas of science that we need more development in to understand this bigger question. Now, there is a bit of a shortcut here, which is that if you were to observe a technological alien civilization, you can get information about F, C, and L, and therefore N, and skip all the other earlier steps. And so that's sort of the other approach, instead of taking it step by step, is to try and jump to the end and see if you see any of the end results of the process, and then use that to work backwards. So philosophically, that's basically what my work is doing. How do we figure out the fraction of stars that are hosting technological civilizations by just straight up looking for them and seeing if we see them? So there are a couple different methods that we use, and I'm broadly grouping these into sort of these silly titles of we listen or we spy. So when we try to find technological life elsewhere in the galaxy, one strategy we use is communication SETI, which is listening for intentional signals being sent our way. Is anyone waving their arms and saying, hey, we are here? If so, it hopefully should be pretty easy to see because they're trying to be heard. The other option is spying, which is that if you're using technology, you're modifying your environment in some way. And so maybe we could see those modifications, even if they weren't really meant as a signal for humans or for anyone else in particular. Maybe we could see another alien species polluting their atmosphere or building solar panels or doing other tasks that have nothing to do with us, but we would be able to observe their consequences. There is a third option here, which I will return to in the second half of the talk, which is, or we shout. We say, hi, we are here. We are humans on Earth. Here we are. Is anyone out there? And see if we get any replies. As you might imagine, that one is much more controversial. That's called messaging extraterrestrial intelligence, or Medi. and I will return to it later. I will just briefly say I engage in the top two and not in Medi at the present time in my career, and I can talk about why later. So my bread and butter, so to speak, in research is doing radio communication SETI. So this is looking for radio transmissions from extraterrestrial civilizations intentionally sent towards Earth. See if we pick anything up. So I'm showing a plot here, but I promise I'll go through it step by step. So the vertical axis here, you can think about as how loud the background is. So up at 1,000 here, this is like standing in a club or a concert and trying to hear your friend talking next to you. Like, it's very difficult to make out what they're saying, even though you know they're trying to talk to you and they're right next to you. At the bottom here, you can imagine that's like standing in a library. If anyone was trying to get your attention, it would be pretty obvious because it's very quiet. You could hear a pencil drop, that sort of thing. And then on the horizontal axis here, I actually have cut off the units here. I don't think that was on purpose, but this is in units of gigahertz, which is a frequency unit. And so here at the left side, this is low frequencies. So you can imagine like a tuba if this was audio. And over here are high frequencies, like a piccolo. So this is sort of the search space that we can explore from the surface of the Earth. Like, which kinds of signals are we looking for? Ones with high frequencies or low frequencies? And how useful is it for us to try and listen? And if you try and listen at these really low frequencies, it turns out the galaxy is very noisy at those frequencies. So it would be very hard to hear someone signaling us at, say, 0.1 gigahertz. So this is 100 megahertz. Down that low, like, we use these frequencies sometimes to communicate with each other on Earth. But if you try to communicate with anyone else out there in the galaxy, you're going to hear kind of the combined background noise of dust and gas and all this other stuff that's emitting there. So it's not a very good place to listen. It's too loud. Then on the higher end, sort of above 10 gigahertz, our own atmosphere is actually very noisy. Water molecules emit and absorb. So that's the H2O spikes here. And the oxygen that allowed life to evolve on this planet, kind of funnily enough, blocks our ability to hear other planets at certain frequencies. So you don't really want to be listening at these really high frequencies, like 100 gigahertz and above, maybe even above 10 gigahertz, because of all the stuff in the atmosphere that's very noisy at those frequencies. So you'll notice that this blue line kind of dips to its lowest point here between about 1 and 10 gigahertz. And this is the terrestrial microwave window. So this is the point at which we can basically consider our atmosphere transparent to radio waves. Things from space can come all the way down to the Earth. Things from Earth can go all the way out to space. This makes it popular for commercial applications as well. If you want to send a signal from a satellite down to Earth, you want to do it in this region where everything's nice and quiet and transparent. But it also makes it popular for SETI searches because any planet with an atmosphere like Earth's should have this nice quiet area between 1 and 10. So maybe that makes it so that between 1 and 10 gigahertz is a popular place to send and receive signals from space. If you want to get even fancier with it, there are a couple of really important emission lines in the galaxy from hydrogen and hydroxyl, that's these two lines here, that are just present no matter where you look. So they should kind of be like universal signposts. If you're in the Milky Way, no matter where you are, you should see these two lines. And so a lot of early SETI searches in the 60s and 70s focused on looking to see if anyone was sending us signals between these two very prominent signposts in frequency. No successes on that so far, which maybe I should have prefaced my talk with, but it's an idea of when you have this huge range of frequencies and places and other things to search, you want to try and narrow it down as much as possible to focus on the places you think have the best chance of success. So as I said, communication SETI in the radio is what I do. So this is an image of me from a couple of years ago. Here I am with my graduate course in SETI. And we took a field trip to the Green Bank Observatory. So this is where the Drake equation was invented. And the Green Bank is a thriving radio observatory in the present day as well. And its sort of prime famous telescope is the Green Bank telescope. And the pictures don't do it justice. I usually say that the dish of the Green Bank telescope is about the size of 2 football fields. I think that works regardless of your definition of football. It's huge. It is the largest steerable structure on Earth, like fixed structure on Earth. And what we do is we use dishes like this that have this huge collecting area to try and listen for very faint signals that are coming from space and going through the atmosphere at these frequencies between 1 and 10 gigahertz, and sometimes a little on the outside of that range. So for example, the sorts of searches that we do sometimes look like this. So on that trip, we performed 6 hours of observations with the Green Bank telescope, and we pointed at stars that we know have planets from other astronomy work from other observatories. And we decided to observe right when the planets were crossing the face of their star as seen from Earth. So if you were looking at this with an optical telescope, or if you had really sensitive eyes, if you were looking at it with your eye, you would see the star being bright and normal, and then after a while it would get dimmer for a bit, and then it would get brighter again. And what we can do is, if we see this kind of telltale pattern, we can infer that what we're actually seeing is a planet crossing in front of the star and blocking out some of the light. So this sort of work is done by space telescopes like Kepler or TESS, if you've heard of those telescopes in the news. And they keep catalogs of all of the different stars that we know of that have planets, and how big those planets are and how far away they are from their stars. So what we did is we picked about 10 Kepler planets, and we observed them while they were crossing across the face of their star. And this is actually one of the observations from that campaign. I've been actually working with that data over the past week or two, so I'm very familiar with these plots at this point. And there's a lot here, but what I want you to notice is just this middle panel that I've outlined in red has this stripe going through it. And this is a narrowband signal generated by technology. Nothing we know in space can generate a signal like that. And there's a reason you haven't seen me in the news saying I found aliens. And that's because if you look at the observations we took right before and right after, so these top and bottom panels, you see continuations of the same signal. And the interesting part is the top and bottom panels are totally different stars. So we pointed at one star, we pointed at the next one, which is the middle panel, and then we pointed at the third one. And the idea is anything that's truly coming from the middle star should not appear in the top and bottom panels. But here you can see the signal continues on, even when we're looking at a totally different star on a different part of the sky. So what we're actually seeing here is some sort of human technology, something like a GPS satellite or a cell tower. And I'll come back to that because that's a struggle for us, is we can easily identify signals from technology, but then figuring out whose technology, whether it's our own noise or something coming from space, gets a little trickier. So I did briefly also want to talk about optical communication SETI, which is not my specialty, but is also sort of a technique that we pursue in parallel with the radio stuff. And I don't know if any of you did this, but when I was younger, sometimes I would imagine like taking a flashlight and using Morse code and pointing at the sky and just like sending signals that way. And like, if you imagine that we had a really big flashlight, right? That seems like it could be a pretty good idea. Look for something that's like flashing with an SOS pattern or something like that out in the sky. Now, the problem with this is, as far as we know, most planets are sitting next to a much bigger flashlight, which is to say they're stars. So if you try to send a message, you just get drowned out by your host star. So for a while, radio SETI was much more popular because stars are quiet in radio. It's as if they're not even there most of the time. But in optical wavelengths, you have to compete with your star, and stars are notoriously very bright. However, stars are very bright at all optical wavelengths. So They're very bright if you look at them with a red filter or a green filter or a blue filter. But if you just pick one of those colors and put all your energy into transmitting at that single color, then you can be brighter than your host star for brief periods of time. So another way to say this is if you use a laser, which only transmits at one very specific wavelength, then you can be seen against your host star. So this is another strategy that SETI researchers are pursuing, is to look for laser flashes in the sky. So here I'm highlighting this project PanoSETI, which is based at UC San Diego by PI Shelley Wright. And Dr. Wright has been working on this really cool idea where you search the entire sky all the time to see if there are any laser flashes. So that's why there's this thing, she calls it a fly's eye design that looks kind of like a compound eye of an insect, right? And so each of these circles in this model are telescopes. So this is like an entire half dome of telescopes, all looking out at the same time and focusing back on detectors so we can monitor constantly the entire sky. So I'm very excited about this project. I think it's very cool. And they're currently in the testing phases. They're testing the lenses that they're going to use for this. They're trying to use mass-produced Fresnel lenses that are usually used in lighthouses. So making use of technology from other sectors as well. And are currently testing out some of the detectors, I think, at a couple sites in California. So that's the communication SETI part of my talk. That's assuming someone wants to get our attention and is sending a beacon our way. How do we detect the beacon? Now, the problem with that strategy, right, is if no one is sending us a beacon, then we're not going to find any. But it doesn't mean that there isn't life out there in the galaxy. So in tandem with those communication SETI searches, we also try to do artifact SETI. So this can mean, like, when you think about artifacts, right, you think about a physical object. And so maybe something like our satellites in the solar system, like Voyager, that we've sent out into space. Maybe somebody else sent a Voyager our way, and we could pick up a physical object and examine it and see that it wasn't made by humans. But this could also come in other forms. Any change that your technology has made to your environment could be detectable if you're close enough or have a good enough instrument. So for example, the night side of the Earth now, because of city lights, looks very different than it did, say, a couple hundred years ago. Our atmosphere looks very different than it did a couple hundred years ago, which is a challenge that we have to face right now with global warming and pollution. But what that does is it adds components to the atmosphere that you can detect from very far away. You can look at the spectral fingerprint of these molecules that we're putting out into our atmospheres, and you can say, that planet has a really high concentration of chlorofluorocarbons or CO2 or other things that are emblematic of some sort of industrial technology. This middle picture here is an artist's rendition of a Dyson sphere. So this is another idea about how we might be able to detect industry from very far away, is that one of the best energy sources we have access to on Earth is the sun as our host star. So maybe eventually we would want to surround the sun in solar panels to harvest as much of that energy as we can instead of letting it go out into space. If you do that, then from far away, people will start to see the star getting dimmer, right? If any other alien SETI project was looking at us and we built a bunch of solar panels, they would see the sun being dimmer or being blocked sometimes, just like the example with the planet transiting in front of the star. And so we might be able to find other technologically advanced civilizations that way, where by advanced, I just mean that they can do a project of the scale, which we cannot do yet. And then on the right here, I have kind of a fun diagram that talks about leakage radiation from the Earth. So it illustrates over time, we have sent radio and TV broadcasts to each other on Earth, but sometimes those signals leak past their intended targets and kind of travel out into space as well. And they're not strong because we're not sending out our TV into space on purpose, But if you have a sensitive enough telescope or you're nearby, you might still be able to pick it up. And the sort of fun thing about this is that these transmissions travel at the speed of light, and the speed of light is finite. So what that means is the further away from Earth you go, if you look back at Earth, you'll see it further and further back in the past, which is one of those kind of fun consequences of the finite speed of light. So I think this graphic now is a little outdated, but anyone looking at Earth from far away would see us get brighter and brighter and brighter over time as we develop more and more radio technology. So maybe we could detect that, the equivalent of alien TV and radio for nearby stars, even if they're not intending to send us those messages. So there are a couple of issues with these techniques. And the first one that I want to talk about is distinguishing between technology and nature, because nature does things that we don't expect sometimes. So here I'm showing an image of Dr. Jocelyn Bell Burnell, who in the 60s and 70s was a graduate student in the UK. And as part of her PhD work, she built an entire radio observatory by hand, basically, which is incredibly impressive. But then after building it, she used it to perform observations of the night sky with the antenna array and the equipment that she put together. And she started noticing that she was finding particular points on the sky that seemed to be flashing very regularly, like once a second, every second, bright pulse of radio emission, bright pulse of radio emission. And for a while, she and her advisor kind of were joking around like, haha, I wonder if these are the little green men. So they called these signals LGM 1 and 2 and 3 for little green men. As far as I can tell from reading the historical reports, it seems like they didn't truly believe that they had found aliens. It was somewhat of a joke. But certainly as the story was picked up in the media and by other people, the alien side of it was played up a lot. And in the end, they ended up connecting with an astrophysics theorist from another university who said, oh, this is exactly what you would expect from my theories of what neutron stars do. So neutron stars are the cores basically of dead stars after a supernova. If they're too small to become a black hole, they become a neutron star. And neutron stars are small, they're dense, and they spin really quickly. And what happens is they have a lot of energy left over from the supernova. And so it shoots out in a jet from the poles of the neutron star. So you can kind of see in this image, which is a combination of radio and X-ray and optical data of the Crab pulsar, which is a neutron star, that there's this sort of jet coming from the bottom left to the top right of the image here. And the idea is that as these neutron stars spin, if you happen to be just along the line of the jet, then you're going to see a flash every now and then as the jet passes over you. So imagine like if you're on a ship and you see a lighthouse, you don't see a light spinning around, you see a flash every now and then when it points in your direction. Exact same idea. So what she had discovered were pulsars, which were neutron stars that are lined up so that we see this pulsing radio behavior. And they are very cool. They're actually my other kind of research focus when I'm not doing SETI, but they're not aliens. And so this is an example of when we found an interesting phenomena in the sky, and there was some uncertainty as to whether this sort of signal would be what we would expect from an extraterrestrial intelligence. This is one of the most popular renditions of Jocelyn Bell's plot, by the way. So the top line here is the first pulse, and then you wait and it wraps around, and then there's the second pulse. And if this looks familiar, it's because this illustration was then used for the cover of a Joy Division album in the 80s. So any post-punk fans out there, I was so happy when I discovered this connection between my work and my music. But moving on from that, the other question that I've already sort of brought up here is, how do we know it's not just human technology that we're seeing? So here I'm showing some data from the Parkes telescope in Australia. And over the course of, I think it was about 5 years, every now and then, the telescope would detect these really bright signals. And they always happened at the same frequency. They'd start at about 1500 megahertz or 1.5 gigahertz. So in that window I was talking about. And then they would drift down. So always the same frequency, but they would appear at different parts of the sky, seemingly randomly. And this sort of shape can only be generated by technology. But of course, because they were coming from random parts of the sky at random times, the astronomers were skeptical. And they were like, okay, like probably this is something like lightning flashes on Earth, maybe mimicking technology, or planes flying overhead, or they came up with all these different ideas for what this could be. And in the end, they realized, it took them years to track this down, but they realized that whenever these things appeared, it tended to be around like local noonish at the telescope, and then about 6 or 7 p.m. And then they were like, okay, what happens around noon and 6 or 7 p.m.? And then they realized that for the staff on site, you know, they live, telescope operators often live on site. They do their shifts and then they come back to the staff observatory building. And I don't know if any of you tend to do this, but if I'm really hungry and it's dinner time and I'm heating up my food in the microwave, sometimes I get impatient and it'll be like 3, 2, 1, and I'll like hit the button right as the microwave timer finishes. Turns out if you do that and you don't let the microwave wind down fully, it sends out a burst of microwave emission. And as the microwave powers down, it goes from higher frequencies to lower frequencies. So these mysterious signals that took years to track down were just observatory staff opening the microwave a little early. And it turns out that it had nothing to do with anything on the sky. Now it's pretty standard for microwaves in observatories to be in multiple boxes deep to make sure this does not happen. So it's not always easy to tell which signals are coming from space and which ones are coming from us. And probably the example of this that is closest to my heart is the aforementioned BLC1. So this was a signal that was detected in 2019, but we didn't actually kind of start and finish the analysis until like kind of last year. And I'm just going to play a video here that shows the start of the observation, a plot that goes all the way from the start to the end. And there were a couple of characteristics of the signal that were really exciting to us. So I don't know how well the animation's coming through, but hopefully you can see that there's like a very narrow yellow line that occasionally appears in this plot, but then it disappears in the narrower panels. So it's there and then it's gone and then it's there. And it's drifting. So it's changing frequency over time, which is characteristic of something on the sky usually. It's only appearing when we're pointing at Proxima Centauri, which is our nearest stellar neighbor. It's narrow, which means it has to be technology. And it disappears for a little bit here. So if you were squinting, don't worry, it actually is not in that panel. And then it appears at the very end again. And so this was something that was persistent for almost 5 hours, which is not usually what we see with things like planes, which go overhead quickly. And it seemed to have all the characteristics of something coming from space. So this example, this single signal, took up about 6 months of my time, full time, to try and track down what was going on. So we compared it to all known satellites that were in the sky at that time. We compared it to the sorts of drift rates we might expect from Proxima Centauri itself. We consulted with the observatory staff to figure out if there was anything strange going on that day, if the microwave had come out of the box for a day, something like that. And in the end, we found many examples of signals that looked exactly the same. Oops, here we go. So they had the same shape. Some of them were at the same frequencies, but the day before and after, some of them were at different frequencies. And all the other examples we found showed up in all of the panels. So also in these narrow panels where we were looking at something else. So that indicates that the whole set of them is coming from Earth. But there were characteristics of the signal, like I pointed out, that made it seem really promising. So sometimes Earth technology does a really good job masquerading as signals from space. And the more technology we have over time, the more crowded the interference environment gets, and the harder it gets to tell what could be an alien signal and what's just the cell tower nearby. So I kind of want to, this is the conclusion of the science part of my talk. I did want to mention that, at least in the United States, the institutes that are doing this work are primarily the SETI Institute, which I'm now at, which is a nonprofit located in Silicon Valley, the Berkeley SETI Research Center, which has been around a very long time, which currently hosts the Breakthrough Listen project, which is the most well-funded SETI project in history. And it's funny because this slide, I've given similar talks before, and every time I have to update this slide because the funding environment is so dynamic. So NSF, through my fellowship for the next 3 years, but also through awarding other projects recently, has gotten in on SETI funding again, which it had not for decades because of kind of political, the political disfavor of searching for alien life in this way. NASA as well, I did not have on the slide for a while, but they also recently have been awarding technosignature grants again, which they hadn't since the early 1990s. So it seems as we learn more about exoplanets, planets around other stars, and we develop more technology that makes it easier to search for life in the universe, some of the bigger funding players are now coming back and saying like, okay, we think actually there's some merit in this. We have the tools to do the search now, and we're going to commit more resources towards it, which is really cool to see. And then I think this is my last note on the science side. How do we do these searches? So from the radio, I showed you like that giant Green Bank telescope dish. So really large single dishes, Green Bank telescope, or the now unfortunately non-functional Arecibo telescope in Puerto Rico, which collapsed a year and a bit ago. That's one strategy. Another strategy is to use a lot of smaller dishes all in coordination with each other, and then they function like a larger dish. So the Allen Telescope Array, which is owned by the SETI Institute, is one such instrument, and this is the one that I work with primarily now. The Meerkat telescope in South Africa is a similar setup of a bunch of smaller dishes all put together. And I also wanted to give a shout out to JWST, which is a space telescope that NASA launched on Christmas Day, which was a very stressful morning for me. This is an almost $10 billion project that we then bundled up, put on a rocket, and sent out into space. And over the last month, it's been in the process of deployment. And so it's been unfolding the sun shield. It's been getting all the mirrors aligned to focus on the detector. This is an optical and infrared telescope. And there are many science goals, and it's going to be very competitive to get time on this telescope. But one of those goals is to try to understand the components of exoplanet atmospheres. Many people using it to do that are focused on looking for signs of, say, oxygen in an exoplanet's atmosphere. But you can use those same observations to look for things like chlorofluorocarbons or ozone or other materials and compounds that might be indicative of technology. So that's a very cool opportunity that's upcoming. And I think the commissioning phase, like over the next couple of months, this telescope will be doing testing, and then it'll start to be open for observations by astronomers. So I think we've been waiting 30 years for this one. So that's a very exciting opportunity that's happening right now. So now I wanted to talk a bit about some of the ethical and policy implications that we think about when doing this work. So I think I have 5 sort of case study examples. It doesn't cover everything, but I hope to give a pretty broad overview of the sorts of connections between the work that I do and other fields, and some issues that we run into. So the first one, and I've sort of alluded to this already, is that the more technology we develop that relies on radio communications, whether that is GPS or our cell phones and devices, our like Fitbits and Apple Watches and whatnot, all use radio transmitters. They all have transmitters in them. The small ones are usually pretty easy to filter out, but satellites are particularly difficult because they're actually in the sky, so they can mimic sources that are coming from the sky, and they are becoming more and more numerous over time. So astronomers are very worried about the rise of mega constellations, things like Starlink. And if you've heard anything about this sort of controversy or fight between astronomers and the industries that are doing this, you've probably seen images like this, which is an optical sky survey. So just a telescope that's taking big pictures of the night sky. And there are these huge streaks across the image. And each one of these streaks is a Starlink satellite going through the field of view of the telescope. And because they're metallic, they reflect light back towards the telescope. So you end up with these streaks, and then trying to do astronomy is very difficult when you have this contamination in your image. However, radio astronomers are also worried about these sorts of satellite constellations because we lose sensitivity wherever those satellites are transmitting their information back down to Earth. So the square kilometer array, which is going to be consisting of actually the dishes that I'm showing here, the Meerkat telescope is sort of a precursor to this square kilometer array, did a study about this and found that the downlink bands for Starlink are the same bands we would use to look for water and glycine in other planetary systems. So these are molecules that we are interested in because they might tell us about the presence of life in other systems. And because that's the band that Starlink has been allocated for their downlinks, if nothing changes, then there are just experiments we can't run with that facility anymore. From a more SETI specific perspective, not astrobiology in general, we just would be unable to look for signals at these frequencies because they're so crowded out with signals that humans are generating. So there are a lot of questions here. This is how I'm going to frame each of these issues, is kind of describing it and then talking about some of the questions we're asking. So there are potentially good uses of mega constellations that could be very helpful to humanity. How do we balance the potential good of any specific project with the damage that it might do to astronomy in dark skies? Something we've been thinking about a lot is this a problem that we can solve with policy solutions? Can we come to the table and say, hey, we're seeing these issues, how do we come to a compromise that works for all parties? In a more philosophical sense, is access to dark skies a human right? The mega constellations that are going up, once all of the planned ones are completed, we're going to see more satellites moving across our night skies than stars. And is that something that is in itself producing some sort of negative value for humanity? And can we pursue technical solutions to interference? This is often suggested by folks on the industry side, saying, well, there are machine learning algorithms you can use to take streaks out of your images, or maybe launch your telescopes into space so you're above the satellite bubble. Are these things possible to do? And if they are possible to do, is pursuing them signaling that we're sort of giving up on the policy solutions? So I promised I would come back to Medi, and here we are. So Medi generally is this idea of messaging extraterrestrial intelligence. And there are two basic ways that this is done. So one of them is sort of the more harmless one, which is that humans like to send kind of fingerprints of our existence out into space. So Voyager had the golden record on it, which very famously was sort of a big international project to portray humanity as a whole. Pioneer, the Pioneer satellite had the Pioneer plaque, which is shown here. The Pioneer plaque is interesting for many reasons, and people have done many analyses of why we sent this particular set of images into space on Pioneer, one of the things that I wanted to draw attention to was the lines on the Pioneer plaque, which you'll also see here on the golden record, which is a pulsar map. So kind of coming full circle, these objects that Jocelyn Bell Burnell discovered are also very good for celestial navigation. If you want to travel through the galaxy, you can use them as markers to navigate as sort of a galactic GPS. And so this is our position. This is how to get to Earth based on galactic positioning. So that information of how to find our planet is out there on a couple of satellites that we've sent out beyond our solar system, not too far beyond at this point. None of these satellites are even to the nearest stars yet. They're just barely getting out of our own solar system. But that's information we've put out there. The other kind of Medi is sending signals. So electromagnetic radiation transmitting "we are here" messages. And as you might imagine, this is controversial. You're sending messages out telling everyone where Earth is, and these messages can travel for light years and light years and could be detectable at the stars that the transmitters pointed at. And what might be the complications? You could imagine, you know, a sci-fi scenario where we reveal our position and then alien overlords come and destroy the Earth. But even without kind of that sort of dramatic popular science influence thinking, there's a lot to consider here, because the problem is there's no kind of punitive measures or anything. There's no treaties in place that govern Medi. So every couple years, another Medi transmission goes out from some group that gets access to a transmitter and decides what they want to send. There was one a couple years ago that was a dubstep playlist. There was, so these are just individual interest groups that pay for time on a transmitter and then transmit whatever they want. This is not regulated. And so Medi, of course, the question at first is, can we regulate Medi transmissions? Is this something that would have to be an international effort? Because in theory, a transmission sent by one person in one country could affect all countries, all people in all countries. Another question that I'm happy to dig into later if anyone's interested is, I think it's easy to see how Medi could be harmful, but given the transmitters that these groups are using, is Medi actually harmful in practice or in theory? So philosophically, is it a problem that people can just send out whatever they want into space? And then practically, do those messages have any hope of being received? And the answers to those questions might inform whether we need to regulate Medi. Something I've been thinking about a lot is, once we succeed, if we were to find an alien signal from space, is Medi inevitable? Is there any way to stop people from sending messages into space once we find life in space? And a framing that we like to think about in SETI is, who speaks for Earth? In the case we did succeed and find some alien civilization or alien intelligence out there somewhere, would we want to send a message? And who decides whether that message is sent? And what is the content of that message? So this is sort of the case of, can we have a globally decided upon Medi instead of these individual actors? Is that possible? Should it be done? Okay, I think I would be amiss if I didn't mention the ongoing colonialism and telescope site choice. So the most famous example of this right now, and you might have seen it in the news a couple of years ago, is that Mauna Kea in Hawaii is one of the best sites for optical telescope construction in the world. When you build a telescope, you want to do it at a high elevation, so you don't have too much atmosphere and clouds in the way. And you want to do it somewhere cold and dry, again, for atmospheric reasons. And you want to do it somewhere away from people. You don't want light pollution from nearby cities blurring out the night sky. And so with all of these considerations, it often is the case that the best sites for telescope construction on the Earth are also sites that are sacred and important and guarded by indigenous communities that are guardians of that land. So Mauna Kea has a particularly complex and deep historical kind of story with astronomy. And so this is not a new issue. This is something that has been a conflict going on for decades. And recently, Hawaii approved a permit to start the building of the 30-meter telescope on top of Mauna Kea. And the 30-meter telescope is an optical telescope with a 30-meter mirror. And so it's kind of hard to imagine how large that would be. I think it's a 10 or 12-story building on top of the most sacred site in Hawaii. So you can imagine that this was not a popular decision by the Hawaiian government, and indigenous Hawaiian groups staged protests and sit-ins that blocked the road that led up to the mountain to try to halt the construction of the foundation for the 30-meter telescope. So I'm happy to talk more about that particular instance, but I mostly talk about that as a case study for astronomy not really engaging with indigenous perspectives very well. This has been an ongoing issue, and it's not just optical telescopes. So I showed you the Meerkat telescope, which is a bunch of dishes in the desert in South Africa, in the Karoo. This is the Karoo, and there's some amount of controversy also for Meerkat and the Square Kilometer Array. So who owns the land that those telescopes are being built on? How do we make sure that we're paying attention to these indigenous perspectives and also the perspectives of any landowners who are interested in that land? This is a bit different for radio telescopes because you often want flat, dry, low places instead of tall, dry places. But this is something we have to wrestle with. So how do we ensure that we're not perpetuating colonialism and just sort of overrunning the will of people who are at these sites, especially when these sites are not necessarily in the countries that are the primary stakeholders in the science? How can we teach ourselves and our students as astronomers and physicists who don't often engage with these questions, the complicated legacy of astronomy and physics, and make sure that we're coming at this with all the information we need and a balanced perspective? And I think there's a bigger question here of how should SETI in particular relate to life on Earth in our pursuit to find life elsewhere? And in case you think this is all sort of detached from the science, some people sometimes treat it that way, but it's not. So how much does the entanglement of colonialism and Western scientific practice bias our ability to broadly imagine alien life and what it would do and what it would be like? So the example I like to give is most pop culture aliens come to Earth to colonize Earth, and you hear those words a lot in science fiction media. How come all of the aliens are interested in that and not something more benign? And that's informed by our media, which is informed by our history. And so if we're more aware of those biases and we try to actively mitigate them and combat them, maybe we'll come up with new search strategies to look for different kinds of alien life that we wouldn't have come up with if we were just mired in this same idea and weren't aware of our biases. I think this is my number 4 point of 5, so we're almost through here. You might have picked up on this when I talked about artifact SETI, but in the case of a physical artifact, a monolith on a planetary surface, or the discovery of something like Voyager, but not made by humans, in the solar system, you get a whole new host of problems because suddenly there's an artifact, a physical object that you might gain an advantage from by analyzing that object. So who owns an alien artifact or has the rights to it? If it's found on Earth, if it's found on the moon, if it's found somewhere floating in space? How can we regulate access to that artifact by all the groups that might be interested in it? How would societies react to an alien artifact, and how much will their reactions be influenced by popular media? I think kind of similar to what I said on the last point, there's this idea that if we were to find something, that it might be harmful. And so you could imagine some pretty negative reactions to bringing an alien artifact to Earth, for example. And there are also real concerns about that, because we have protocols in astrobiology called planetary protection. And the idea here is we don't want to bring Earth microbes to the moon or Mars and have them kill off all of the life there before we study it and understand it. We also don't want to bring harmful microbes back from space to Earth. So to monitor both of those things and make sure we don't contaminate between planets, we have this thing called planetary protection. But in general, planetary protection protocols are for exactly the situations I described, like try not to bring microbes between surfaces in the solar system. Are they strong enough to handle the additional complications that might come from an alien artifact? If there's a USB drive on a satellite, do we have a protocol that says maybe we shouldn't plug that into any of our networks? This is something that I don't think has been thought about almost at all, but certainly not enough. So finally, the big one is, what if SETI succeeds? What if we find the signal? What then? So I already mentioned this one, but does Medi become inevitable? If I, succeed in the search that I was telling you about earlier of those planetary transits and find a beacon that came from one of the planets, and I say there was a beacon from Kepler 992b, suddenly is everyone going to be sending signals towards 992b? And is it my responsibility as a SETI scientist to try to contain some of that activity or mitigate it somehow? How will a SETI detection affect societies on Earth? There needs to be more work on this, but preliminary work suggests likely not as much as you might imagine. There have been cases where for a while the public thought that we had discovered aliens, whether that be microbes in a meteorite that came from Mars, that was a big one in the 90s, I think, or maybe it's what happened with the LC1, which is where it got reported before I'd finished the analysis. And people were like, oh, is this the alien signal? And in general, the impacts from that are pretty low because there have been a lot of false alarms, so to speak, in astrobiology, and none of them seem to have caused any earth-shattering consequences. But at the same time, how does that change if it's real? What will a successful SETI detection imply about the place of humanity in the universe? This is more philosophically and from a theological perspective. What are those implications? And should we be concerned about what that's going to do and try and preempt some of those questions that will come up? And how will we mitigate our own anthropocentrism in interpreting what we see? It's very easy if we see a couple of data points that imply the existence of alien life to say, oh, the aliens are clearly doing this, because they are like this. But of course, trying to apply that logic between other humans, even trying to apply that logic to, say, picking a gift for a best friend or something, doesn't always work. So on Earth, we're very bad at understanding what people from different cultural backgrounds are going to do across the globe in certain circumstances. So how can we possibly predict what alien life is going to do if it doesn't even share the same evolution or DNA or anything else that we have as kind of shared ground among life on Earth? I do want to end this section by saying there are social scientists who practice in SETI. There are people who have been working on this since the beginning of the field for decades. So there is literature on almost all of these topics that I've brought up, but it's pretty sparse, and funding is even more difficult than for the hard sciences part or physical sciences part of SETI. So I don't want to make these sound like they're completely open questions that haven't had any thought, because they absolutely have, and I'm happy to provide references for all of these different points I'm bringing up. But we definitely need more engagement from social scientists, from policymakers, and just in general, we need a little bit more of a will for collaboration between all of these groups, because as you might have encountered in the past, physical scientists can be kind of snooty about other fields, especially social sciences. And this is a problem because we need the input of social scientists. And so getting these groups to work together is not always easy, but it's definitely necessary. So I'm going to close with just a short explanation that you might have been thinking about through this whole thing. It's like, okay, if SETI's been around since the 60s, where is everybody? Why haven't we found aliens yet? So there's actually what I think is a very elegant solution to this question. And I always try and share it in my talks because I think it's important. So imagine that we're trying to find life in space, right? Which is this huge, space has a lot of space in it, huge search space. So I'm going to use an analogy. Like imagine that all of space is equivalent to all of Earth's oceans. You're trying to find life somewhere in all of Earth's oceans. It's a lot of water, right? So when we do SETI searches, we're basically taking scoops at a time out of the ocean and trying to say, like, is there any life in this scoop? And at this point, we have searched maybe a small swimming pool's worth of the search space. And so my mentor, Dr. Jill Tarter, likes to say, well, if you took one swimming pool out of the ocean and you didn't see any fish in it, would you then say, okay, I guess there are no fish in the whole ocean? Probably not. So the reason we haven't seen anything yet is because we've barely started searching. And even though it's been going on a long time, kind of in human timescales, 60 years, right? At the beginning, we could only search basically like a quarter teaspoon at a time. The tools and technologies weren't developed enough. Now we can search hot tubs at a time. And so actually, since I made this talk, we're probably at a couple swimming pools. So this amount that we're searching is really accelerating. And most of the searching that's been done has been done in the last couple of years by the Breakthrough Listen project. So a single project can make a huge impact on the field at this point. And there's a lot more to do. So to close, this slide right here is an image of all of the exoplanets that we knew about in 1995. And lest you think my slide is malfunctioning, this is accurate. In 1995, we didn't know about any exoplanets. The only planets we knew were the ones you learned maybe in like a planet song growing up, Mercury, Venus, Earth, Mars, etc. Depending on whether you count Pluto 8 or 9. And now that picture looks more like this. Thousands and thousands of exoplanets have been discovered. A couple days ago, the telescope TESS, which was just launched, I think in 2018, has now found over 5,000 objects of interest, which are mostly planets, probably mostly going to be planets. So I think we're approaching 10,000 known planets now, within a couple decades of searching. But the problem was before the 90s, we didn't have the technology we needed to pass the threshold where we could actually detect these. So it looked like the sky was empty, but that's just because we didn't have the technology to find them. Similarly, there's this particular phenomenon called a fast radio burst, discovered at Parkes, not microwaves this time. And in the year 2000, this is all the fast radio bursts we knew. It was not something that we had ever detected before. And now, especially in the last even year, we have a couple hundred of them that we know about. And some places on the sky send out these radio bursts very regularly. We don't think these are aliens, by the way. We think these are the centers of galaxies or maybe neutron stars doing something weird. But there's still a lot to learn about these objects. But something kind of cool about this example is we actually did have the technology to detect them for a while before they were detected. They were just in a weird part of parameter space, and no one expected there to be objects in that part of the parameter space. So they weren't using the telescopes in that way. And as soon as we kind of flipped the switch and someone was like, I wonder what happens if we just search like way, way, way beyond anything we've searched before. Like, we don't think anything's supposed to be there, but let's try it. Suddenly these things appeared. So maybe we do have the right technology and we're just not using it in the right way yet. So with that, this is my slide on all of the extraterrestrial intelligences we know of right now. And I hope sometime in my career I can hit next on this presentation and show you something about the prevalence of alien life in the galaxy. But for now, I will leave it there. So thank you so much. This is a lot of talking, I know, but I'm happy to continue the conversation and looking forward to answering questions. So thank you.
Thanks a lot, Sophia. That was amazing. I thoroughly enjoyed it, and I think I'm speaking on behalf of everyone here. It was so clear, I don't know. I mean, it was just pushed our horizon so far, and both on the science and the ethical parts of the talk. So I'm very grateful, and I'm sure there's a lot of similar sentiments in the room. I myself have a few questions, but I will reserve them for the end of the session. I'd like to give my colleagues the opportunity to interact with you. So I'm turning now to the room. Are there any questions? Anyone wants to start us with a question or comment to Sophia? Okay, I can see Marina and then Philip.
Hi, Dr. Sheikh. Thanks a lot for the talk. I was wondering, for most of the talk, you've mentioned whether SETI succeeds and also that there's increasing funding. So can you hear me okay?
No, we don't hear you very well, Marina.
I'll write it down.
Okay, thank you.
Let's see, I couldn't hear that particularly well, but maybe you could put your question in the chat and then I can answer it from there.
I think I saw Nicola mentioning my name, but I couldn't hear him. But can you hear me?
Yes, I can.
Perfect. Well, thank you so much, Dr. Sheikh, for the presentation, which I also found very clear and super interesting. I've been very fascinated with SETI since I was a little kid playing Sid Meier's Civilization 2, where SETI features as a wonder of the modern world to boost your civilization science. I would like to come back to some of the high-level questions that you asked. You mentioned that how we might think about an alien encounter is very much shaped by Western media, Western perspectives, especially here. One of the theories that I think got a lot of prominence in recent years actually comes from China, this dark forest theory. I don't know if you've heard of it. I mean, gained prominence with Qin Liu's book of the same name, and then I saw it picked up in some more or less serious documentaries. So I was wondering, is this something that researchers at SETI talk about at the coffee machine, and what does it tell us about how people perhaps in other parts of the world in China might think about alien contact as opposed to they might think about it in Europe or North America?
Yeah, that's a great question and a great point. And I have certainly actually had people come up to me at conferences and ask what I thought about the idea in the dark forest. And so it's very pervasive even within kind of technical SETI circles as well. And I think that's promising. I think it's a move in the right direction, that now we've reached a point where we are having discussion between international communities, people from different cultural backgrounds, thinking about alien life. A lot of kind of that portion of my talk was inspired by a recent issue of the American Indian Culture and Research Journal, which was dedicated to SETI and the search for life elsewhere. So this was 7 or 8 articles written by Indigenous scholars about SETI and how different Indigenous communities view alien life. And I had never encountered ideas like that before. And so I think the fact that we're seeing publications and literature, like you were saying, in serious fora, we're now discussing ideas that are coming from these non-Western perspectives. And in many cases, they're different. They're bringing new things to the table. So in the Indigenous perspective, I think Lakota tradition specifically, as I learned from that issue, the alien is not seen as hostile at all. It's seen as benevolent. So it's scary still, it's unknown, but there's a cultural toolkit to deal with the alien and the unknown, and it's always treated as something that is trying to help humans. So that's, I think, a very different perspective than, say, the dark forest theory of like, we don't see anything because it's scary to announce your presence because something might happen to you. And I think it's important to get that breadth from as many different human perspectives as we can so that we can develop our search strategies with those perspectives in mind and might find these new areas of parameter space and things that we've overlooked that are already in our data, for example.
Great, thanks. Then we have Giacomo.
Yes, so let me really thank you, Sofia, for this really nice and interesting and engaging talk. I'm an economist. So I have a couple of questions and probably more curiosity. So at some point you mentioned the attitude towards the decision whether to announce potential discoveries. I would like just to know whether there are protocols on that the scientific community has agreed upon. And so whether in your group, for example, you have some specific attitudes towards announcing discoveries. I can imagine serious announcements having strong impact on, let's say, stock markets as a minimum, as an immediate impact. And so who is deciding about these protocols in announcing the news? And another thing that would be interesting to know is who is actually investing the most on SETI nowadays? So which countries, and whether it's mostly public or it's also, to your knowledge, private investments?
Sure, those are all great questions. So happy to talk about that. So on the first side about protocols, there have been some more SETI guidelines, I guess, for what to do in case of a detection. And so these have been put together, for example, by the International Astronautical Association, I think it is, IAA, and at the IAC, the International Astronautical Congress. So these are multinational astronomy bodies that for a long time had a very strong SETI presence and now maintain a SETI presence and are one of the main places that scholars in the field get together and discuss these sorts of ideas. And so there is, I'm trying to remember the name of the protocol, but it's basically a guideline that says, if you detect alien life, the first thing you want to do is confirm that you're seeing what you think you're seeing. So make sure your standards of evidence are very high, publish in a standard scientific journal, so that it goes through the same rigorous process as anything else. And at that point, that's basically as far as we've gotten with any SETI detection. But as part of that release, if it is determined, like a detection's confirmed by multiple groups at multiple sites, then there's also guidance about like engaging with the media and making sure that all of the data is, say, public, making sure everything is open access and as transparent as possible. But I think the most recent sort of update to those guidelines is still over a decade old. And of course, now things are different because we have social media and news travels fast, and just the landscape of how people communicate and get their information is so different. So I think there's definitely some needed revision to those policies, and they're not binding. It's just sort of a group of international scholars got together, decided on these policies, which are good, but there's no enforcement, there's no requirement even that anyone in the field reads them or abides by them. So that's tricky. And I do also want to make the distinction between, this is something people get confused a lot, is the SETI Institute is a nonprofit where I'm currently working, but SETI as a field is spread out. And I mentioned kind of the different funders in the US that are invested, but there are groups all over the world doing this. And this kind of leads into your second question, I think, is that in the United States, for the most part, SETI funding is private right now. There are a couple of investors that have invested billions of dollars in the search for life because they find it interesting as sort of a curiosity humanitarian philanthropist investment of money. There's also some level of public support through institutions like the National Science Foundation. But right now, for example, in the Astronomy Decadal Survey that guides the priorities of astronomy every 10 years, there were maybe 3 or 4 mentions of SETI within like hundreds, almost 1,000 pages of text. And none of those said explicitly like NASA and the NSF should fund SETI. And that decadal came out a couple months ago. So for the next 10 years, at least, there's no guidance for US government organizations to fund SETI specifically. Astrobiology in general, there's a lot of support for in that document, not SETI in particular. So it'll sort of be up to individual discretion of people at the agencies, whether that's something they want to pursue. Internationally, I don't know the landscape quite as well. So the FAST telescope in China is the largest single dish telescope in the world right now. And one of FAST's main missions is the search for extraterrestrial life. So for example, the Breakthrough Listen collaboration works with some of the FAST scientists to share software and help analyze data, but it's also, the protocols are very different there, where data takes a while, and there's certain parts of the data that we can look at and certain parts that are restricted to Chinese scientists. And then I know also Europe has a pretty strong network of SETI scientists as well. I think SETI Italia might be the largest one. But again, I don't know the landscape quite as well, and there's not too much collaboration except at, say, the IAC, like in these international bodies. That's when collaborations happen. But in general, most of the papers are written by groups of authors in their respective nations. I have heard that in Europe, it's relatively difficult to get astrobiology funding, even for searching for microbes, and it's even harder to get funding to search for technological life, but that's more anecdotal than anything.
Okay, thank you, Sofia. So I'm going to read 2 questions that appear in the chats. There's the question from Marina, and then there's a question from Teresa. So the question from Marina is the following: after the well-deserved thanks for your talk, the question is the following, quote, "For most of your talk, you have mentioned implications arising if SETI succeeds, but have recognized that so far ETI has not been found. I'm curious how success, other than the ultimate goal of finding ETI, is measured in the field. For example, vis-a-vis the stakeholders that you have mentioned are active in the funding environments. So how do you measure success in what you're trying to do?" The question from Teresa is about something that we, I think, as social scientists confronted with, say, space press news and popular science, we have a problem to understand the significance of. And so the question of Teresa is, how convincing do you find Haveloop's theories about Oumuamua? And so there was a book last year that was published, and there was a lot of talking about the book in beyond the hard science, but we'd like to understand how in your field this is this work is estimated and understood.
Yeah, so 2 great questions. Again, I'll start with the first one. So that's a question that we get asked in our funding proposals a lot, is you say you're going to do this search where you look for signals from extraterrestrial intelligence. So far, you haven't found any. Why should we give you more money to do the search? And if you don't find anything, then is that just kind of money on down the drain? And so we always have to justify that when we're putting in our proposals and discussing our work. And so there are a couple of different answers to this. I think the easiest one is to say that every time we do a search, we're looking in a different part of the parameter space that has never been looked at before. We're looking at new frequencies, or we're looking at stars that we haven't targeted before, or we're looking for, say, weaker beacons. Like when we looked at Proxima Centauri, we could have seen something the equivalent of like aircraft radar or military radar. Again, even if they weren't intending to send a signal, we would have picked it up if it was there. So the more searches we do, the more confidently we can say extraterrestrial life is not doing this particular thing. And, you know, it seems like a drop in the bucket to start, like, oh, Proxima Centauri doesn't have any aircraft radar between 4 and 8 gigahertz isn't the most exciting newspaper headline. But as we do more and more of these searches, those examples kind of start to stack up, right? We can start saying like, okay, it doesn't seem like any of the nearby stars have transmitters on them. And then you can say like, okay, well, if Earth is the only planet within 100 light years that seems to have radio technology, what does that imply for how common it is in the rest of the galaxy? So we can start sort of extending those results the more we search. So it's one of those sciences that's kind of difficult because it's long time scales and lots of space to search. So it's going to be a lot of negative results for a long time, probably. Not guaranteed, right? I could find aliens tomorrow, but in all likelihood, this is an endeavor that we have to be in for the long haul. And so it does make it difficult to communicate the importance of our search. However, there's another answer to your question, which is that SETI has always been on the cutting edge of technological development, whether that's distributed computing with things like SETI at home, or the detectors that we're building now that can detect things that are finer in frequency resolution, so narrower than anything in the past. And then you can use those instruments to look at other objects, pulsars, or like gas distributions in the galaxy, and try and understand other astronomical questions. So when I showed those fast radio bursts, that was an application of machine learning to breakthrough listen data on fast radio bursts, discovering more bursts from that one position on the sky than anyone ever had before. So as we develop technology for the search for extraterrestrial intelligence, we also make advancements in instrumentation and data science and algorithms that can be applied to other parts of astronomy and even beyond astronomy. So I think that's sort of a really nice auxiliary benefit of SETI that keeps interest pretty high, because there's been a really good return on investment for just other things that have come out of the search, even if it isn't yet a discovery of extraterrestrial life. So as for the second question there about Oumuamua, I can say, as an astronomer from reading the literature, I do not believe that Oumuamua is an alien spacecraft. So it seems like the evidence has pointed towards this being some sort of interstellar comet. So we're sure that it came from outside the solar system. That's true. But we believe that this is basically a rock that was ejected, a shard of planet that was ejected during a collision maybe between two planets somewhere else in the galaxy, and got shot out and eventually found its way to our solar system, swooped through, and is now on its way back out again. That's fascinating. Like, that's a really interesting story on its own. And the cool thing is that with sort of upcoming surveys, I showed that image of the sky survey with the streaks through it from Starlink. With surveys like that, we're going to find more and more objects like Oumuamua. So there's already been another one, 2I Borisov, I believe is the name of it. That's another interstellar object passing through the solar system. So I think we're up to 2 or 3 of them now, and we should find many more in the years to come. So I don't think that particular object is evidence of alien technology. I don't find the evidence convincing for that. However, solar system SETI I've talked about is a real part of the field. Like, we don't know our own neighborhood super well yet. So I think people unfortunately like conflate Oumuamua with being indicative of the whole field. And even though that one object is not technology, I think we should have a way to look at the things coming in and say, like, is this consistent with being a rock, or is this metallic or something like that? That's something we should develop, because even if it's not metallic, right, we'll learn more about what these objects are composed of and how they get ejected from their systems. And that'll tell us more about how planetary systems form and how life might evolve elsewhere. So I think they're fascinating objects, and I think there is a really cool SETI angle of them. But Oumuamua in particular, Oumuamua, I'm not convinced. I think we found a very cool comet passing through.
Well, thanks, Sofia, for addressing both questions head on. And maybe, you know, the upside with this work on Oumuamua is that it sort of, you know, generates interest towards more understanding and a realization as well that it's a very complex thing to explain. Giovanni, my colleague Giovanni Sartor, has a question.
Thank you very much, Sofia. I enjoy very much your talk. Just two curiosities that came to my mind when listening to you. First of all, when you started your presentation, you had all those, you addressed a bit the kind of estimates that are done concerning the existence of extraterrestrial life or technology. And you said that there is, we cannot say much about that. But maybe I would like to know what is your view about that on the basis of the scant evidence we may have. And then my second question concerns a bit the time frame. So we have to, when we have to imagine what we would do if we had some evidence of extraterrestrial life, maybe the messages that we get are very much located in the past, maybe, I don't know, thousands, I don't know, millions of years ago. So how this does this temporal dimension affect the way in which we may react to this kind of information? Right.
So let's see, I'm trying to remember the first question. Sorry. So
no,
could you repeat it? Sorry.
It was on what is your belief concerning the existence of extraterrestrial life, even though the calculations that have been done so far are not very, on solid basis.
Right. So the way that I think about it is I think I have a view that's pretty similar to a lot of astrobiologists, which is, okay, you can't tell anything from one sample. But as far as we know in astronomy, there are very few objects that we find that only have a single example out in space, right? We found a couple pulsars and then now we found thousands. We found a couple exoplanets and now we know they're common. And so for me, just sort of on a philosophical basis, in the past, whenever humans have said, oh, we think that Earth is special or the solar system is special, that, you know, everything revolves around the Earth very early, it's never turned out to be true. And this is definitely more of a philosophical point than a scientific one. But based on that, I think I come into this saying that I would expect that there's nothing particularly unique about the phenomenon of life throughout the universe or the galaxy. That if we have one example here, I don't see any reason there shouldn't be more examples out there. That said, I think there's a document, I believe, first authored by Carl Sagan that ends with saying the only satisfactory search for the only satisfactory way to understand the prevalence of extraterrestrial life is to search. The only test is an experimental one. So even if philosophically I lean more to the, I think life should be out there, but I'm curious to see how prevalent it is. Like, the only way to understand that is to actually perform these searches. And maybe the experiments will be done and we won't find anything. And that's also interesting. That tells us about the prevalence, which is that it's rare. So I don't think I'm very tightly kind of bound to this idea that there has to be life elsewhere. But my inkling is that there probably is, just on a philosophical basis, and that makes it interesting for me to search for it.
Sofia, I might have two questions for you.
Nicholas, sorry to interrupt. There is also a question from Stefano Pelli in the chat. So just
oh yeah, sorry about that.
Before.
No, of course.
Thank you.
Yes, there's another question from Stefano Pelli. Let me go up. Yes. Okay, so the question is the following. What is your view about the now standby, as far as distributed data analysis is concerned, SETI at Home initiative?
So SETI at Home, I think I mentioned a little bit ago as well, was one of those things I think I came into it a little too late for it to like inspire me to get into SETI, but I was aware of it as sort of a citizen science way for the public to participate in searches. And as of right now, SETI at home is essentially dormant, I think. It's not sending out any more data. But it's a very, very cool project. And so many people that I meet say that they knew about it or participated in it. And it was an awesome way to involve the public. And at the time, it also was a great solution to the computing power needed to perform these searches. Now it's much more common for organizations like the SETI Institute or Penn State University to have their own clusters, compute clusters on which to run these sorts of analyses. And in some ways, it's more efficient to do it that way now than to send little chunks of data to a bunch of smaller machines. But I think, as we've seen, even with the rise of, say, crypto mining, you can solve the problem either way. You can have a giant server room where you do all your calculations, or you can have miners on a ton of little machines. So both approaches have value in how we come at problems that require a lot of computation. I don't know of any other plans right now to do something like SETI at home. I have vague plans over the next year to try to get a citizen science project going where volunteers can look at plots and say, yes, I see something only when we're pointed towards a certain star, or no, it seems like interference, something like that. So that's something I'm interested in, is trying to get that sort of excitement that came with SETI at home, but through maybe a different way, having the human eye or human judgment involved in the scientific process, because I think that makes it more valuable for the users, for the public who are participating. And also, humans can still do things that computers struggle with, especially when it comes to computer vision and recognizing patterns and structures and images. So I think there's a lot of science benefit that comes from involving the public in a distributed way, but it might not be in the same distributed computing way that SETI at home was a couple years ago.
Great, thanks a lot, Sofia. Again, okay, so I'm going to throw my question now. In fact, I have, I think, 10 questions, but I'm going to try to make them, or sort of summarize them and synthesize them. So one is about maybe some, more philosophical or methodological issues. And so I think, what I understood, but maybe I misunderstood, is that you seem to proceed from the assumption that any intelligence or form of intelligence would develop technology. And so I was wondering whether this assumption or conjecture was in itself open to challenge in your community. The second question that sort of came to mind and flows logically from the first is how you define technology. So I know of multiple definitions of technology, and oftentimes in philosophy, in the old Greek philosophy, it was defined as an art or some sort of craft, action upon the environment. And so I was wondering how you would define technology. You touched on it when you talked about the difference between technology and nature, but I would wonder how you would define this in a positive way. And then that sort of brought in the comment you made about Professor Loob's work, where you said this is a rock, but maybe this rock is in itself a technology. We have no way to, unless we have a very operational definition of technology, we have no way to counter argue that this rock is not a technology in itself. And so going to the last segment of this question is another sub-question, which is, what if we are here trying to define technology by the physics that we know? And so in other words, we are thinking about technology as proof of extraterrestrial intelligence based on our established knowledge of what we can measure. It's a bit like Isaac Asimov in Foundation, where he talks about the mentalists, and that they have a very different technology that the first foundation could not ever fathom. So this is, in essence, the sort of thoughts that I had, and I'd like for you to talk to that.
So I think I'll start out with another quote, actually, from my mentor, Jill Tarter, which is, "We reserve the right to get smarter." So right now, we do have this very narrow view of like, okay, this is what we know of based on how technology developed on Earth. These are the things we're capable of. We could imagine that other alien intelligences would develop the same thing, maybe slightly different, maybe slightly bigger. Let's look for that. So you're right in that maybe, you know, they're sending us messages in neutrinos or some particle we haven't even discovered yet. And it's just, we're not sensitive to the things that they're sending because we haven't even conceived of that physics or technology yet. That's definitely possible. But in science, you kind of have to operate on your knowns, your observables. And so that's why we do things like looking in radio waves. And we often get these questions about like, but what if you're looking in a totally wrong way? And it's like, we could be. That's definitely possible. But if we look in radio waves and don't see anything, that still tells us something. It tells us they're not using radio waves, whether it's because they're not there, or whether it's because maybe the planet we're looking at has very intelligent dolphin-like species that have an Atlantis-like city under the ocean, but don't build radio telescopes. Like, that's a possibility, right? Or maybe they're so far advanced that they don't use radio telescopes anymore because that's archaic. Why would you do that? Definitely possible, right? But the other thing is we tend to look for technologies that are commensurate with our own. And so I think this also speaks to your question, where it's not like we're not interested in the dolphin civilization or not interested in finding octopi on Europa or something like that. We totally would be. The problem is a problem of technology and detectability, where unless we can come up with a way that we could see those octopi or that dolphin civilization, there's really nothing science can do to try to find those. But there is something that science can do if there are radio transmissions, because that's something that travels at the speed of light that we know how to do, that kind of cuts through the galaxy without being blocked by dust. They're relatively cheap to produce, radio waves. So we have all of these reasons that we choose the technologies that we look for. Always open to more suggestions, but the things we look for are as well grounded as they can be in the physics we know right now. They're the best choice given what we understand. That could change, and then our techniques will change. But as far as we can tell, searches for radio waves, searches for lasers, looking for artifacts are still kind of the best techniques that we have right now. As for a definition of technology, if you're curious, I actually have a long kind of digression about this in the introduction to my thesis. This is a paper that I want to make kind of its own standalone paper at some point. And I ended up getting kind of nitpicky in my definition, like, oh, a tool using animal has to use a tool to create another tool, and it has to be not attached to its body like spider silk, and do beaver dams count? Do birds' nests count? Like all of these sorts of considerations. So I do address that in my thesis, and I won't go into the whole discussion here. But it's difficult to define technology. But similarly, it's kind of difficult to define technology for things that are on the borderline. Things like, is a termite mound a technology? Is something that sometimes people will talk about in my field. But in the end, if we can't detect termite mounds on other planets, does it matter? So I think this is more interesting when we think about the solar system. If we found a termite mound on Mars or the moon, then we have to come back to this, because that's something we can actually detect and investigate, these in situ searches. But as far as detecting life on other planets, we wouldn't be able to see beaver dams or bird nests or termite mounds. And so the point's sort of moot in that way. It's fun to think about.
Thanks a lot. That was very helpful. And it's going to keep me thinking more. I don't see any other question. I had two more pointed questions for you. We still have 5 minutes. If I may abuse these marginal units of time that we have to enjoy your presence with us. So one was when you talked about the policy implications, and so the sort of lack of governance, clear, who's speaking for the international community. Is the United States the leading voice, and are we going to have Jeff Bezos and Elon Musk speaking for the world in the future, and that sort of stuff? And so I was wondering, what your standpoint is about when we should deal with these issues. So there's often this question when we talk about politics and law about, okay, don't move too fast because you're going to stifle innovation with, norms and rules which are going to influence the trajectory of research. So when should we intervene, and what would you say are the priority items on the list? Maybe we don't need to deal with everything. So that's the first question. Second question is even more pointed. There's a lot of sort of public interest towards space these days. Is this helpful for your own research, or is this adverse in some ways that we might not really think about from the outset?
So I think those two questions are related in that a lot of the public interest in space is driven by these single actors who have a lot of power in kind of space industry, right? And so all of the interest in space is interesting. I've definitely noticed it over the past couple of years. When I tell people what I do and talk to people, they're like, oh, I saw something, like, it seems like space is everywhere now. Like, I saw in the news, like, all these rockets launching, and with Oumuamua, like, that was a big thing that came up a lot. And so the public's paying attention, and I think public awareness of space and space issues is great. Unfortunately, I don't think that translates very well to an understanding of my work or funding for my work, because a lot of the sort of interest in space is driven by space industry right now. And space industry doesn't invest in SETI. And in fact, some of the things they do, like these mega constellations, are pretty harmful to SETI and other astronomy from the surface of the Earth. And if we think even further into the future, a lot of the stated goals of space industry are to do things like mine asteroids or colonize the surface of Mars, which is a phrasing you'll hear. And those sorts of activities also, if there's any biosphere or any like subtle or small artifacts in these places, there are no protections for those things to make sure we're not bringing Earth microbes out, these planetary protection issues. So I think in many ways, the push to accelerate space industry so quickly and in kind of an unregulated way, because it's driven by these individual actors, can be very harmful to astrobiology. And it doesn't have to be that way, right? I would love to see a space industry and astrobiology working more in tandem. But to do that, I think it would have to slow down a little bit to think about, okay, what are the implications? How do we make sure our contamination protocols are good? How do we make sure these satellites aren't going to harm astronomy before we launch them? Those conversations aren't happening. And so as it is right now, the public interest in space is good and it's fun, but it doesn't tend to translate into benefits for astronomy and astrobiology, which I don't think is necessarily obvious, especially if you're not in the field. And then I may have given away my answer, but I think we need to start engaging policy and law and experts in these social sciences sooner rather than later, as soon as possible. And it's possible that that might slow down some of what we're doing. I think the groups that would be most affected, at least at first, would be groups like Medi International, who are trying to send out messages. That's probably a good place to start with thinking about how to regulate what's going on. But because most SETI is done just by listening, there are some controversies on saying just listening with all of the kind of movement of resources and capital that implies. But I think the kind of traditional SETI enterprise wouldn't be affected so much by additional regulations on what to do for post-detection protocols or thinking about Medi and sending out signals. I don't think additional regulation there would slow down the science too much, and I think it is necessary. And we definitely want to start thinking about it before it's necessary to use these protocols and refer back to them. So I think updating those especially for the modern world with social media, for the world also in which technology is cheap enough that it's pretty easy to get your hands on a transmitter that could send signals across the solar system or even between stars. Like, the time is now to start thinking about those questions, and we would definitely prefer to think about them sooner rather than too late.
Great, Sofia. And, you know, as much as we can contribute to that discussion, we would be happy to play a role. So there's lots of people here, and we have our eyes on law and regulation and policy issues. So if you need people to talk to in Europe about, you know, how to approach the European institutions, for instance, we can help build bridges. Okay, so it's time to close this event. A bunch of people had to leave, but they left nice messages in the chat. We'll debrief with them here, but it's a safe bet to say that it was absolutely amazing, and I learned a lot. There's one last question I wanted to ask you, which is whether you read or watched science fiction works, and which ones were your preferred items. But maybe we can talk about that bilaterally when we close the talk. All right, Sofia, so thanks a lot. Warm applause from our side. And yeah, we hope to catch up soon and maybe meet in person one day.
All right, fantastic. Thank you so much for inviting me. This was a lot of fun for me as well.
Thanks a lot. Thank you.